In this video, we're going to take a look at a type of organic reaction called a nucleophilic substitution reaction. But before we get into that, we need to define what is a nucleophile, and we also need another term, electrophile. But let's start with nucleophiles. So nucleophiles are electron pair donors, or they're also classified as Lewis bases. Now, when they react with something, they can form a coordinate covalent bond. So really what you're looking for here is something that has a lone pair of electrons. So if you think about transition metal complexes, all of those ligands are Lewis bases. And in terms of organic chemistry, some of the common ones we have are water. So water has a lone pair of electrons, well, a couple of lone pairs of electrons on the oxygen. OH minus is another great one. So lone pairs of electrons on the oxygen. Ammonia is another example. There are lone pairs on the nitrogen. The cyanide ion, lone pair of electrons on the carbon. There are lots and lots of examples. So even halogen ions could be examples. Hydrogen sulfide ion is another example. So there's lone pairs of electrons on the sulfur. And these are all really great examples. So even some derivatives of ammonia are some typical examples, like methylamine is an example of a nucleophile. So what I'm really trying to get at here are there are lots and lots of potential nucleophiles available. So electrophiles kind of go with nucleophiles hand in hand, and they're essentially the opposite of a nucleophile in that they are electron pair acceptors, or they're Lewis acids. So for example, if we think about transition metal complexes again, the transition metals are the Lewis acids, whereas the ligands are the Lewis bases. Or the transition metals are the electrophiles, and the ligands are the nucleophiles. So really, electrophiles are called electrophiles because they're electron deficient. They typically have either a positively charged ion or they'll have the positive end of a dipole. So some examples of electrophiles is, for example, a carbon-carbon double bond or even a carbon-carbon triple bond. HBr is another example, so that has an end, a positive end of a dipole. NO2 plus is another example. There are lots of these. So H plus is an example, CH3 plus, pretty much anything, right, that has a positive charge or has a positive end to its dipole. So HCl has a positive end, HBr has a positive end, and so on. The one other one, also a carbonyl group. The delta plus is on the carbon, so we have a dipole there as well. So nucleophiles and electrophiles kind of go hand in hand together and work together in various different types of organic reactions. So one such reaction is the nucleophilic substitution reaction. So just in terms of generally what this particular reaction is we have a nucleophile. So the Nu means nucleophile with a lone pair of electrons. So this is really important. And that lone pair of electrons, this curly arrow means that two electrons are attaching an electrophile. So this is our electrophile. And when it does that, it kicks out electrons that are bonded to a leaving group. So X is a leaving group. And so what we're essentially doing is we're creating a new bond between the nucleophile and the electrophile. And the leaving group is leaving. That's why we call it a leaving group. So let's look at a couple of examples. Let's look at something very simple. We can do chloromethane, so that's CH3, CH2Cl. And if we react that with an OH minus, that is our nucleophile. It has a lone pair of electrons on the oxygen, so it's going to attack the carbon that's attached to our leaving group, and then our chlorine is going to go bye-bye. So what we're going to end up creating here, it's a substitution reaction. So we're substituting the chlorine with our nucleophile, and our other product is going to be our chloride ion. We can do another similar. So let's take we'll take 2-bromopropane. And this time let's react it with an SH minus. Okay, so knowing we've got a lone pair of electrons on the sulfur here, we're going to replace the bromine, and the bromine is going to leave. So we're going to create this molecule here where we now have an SH group instead of a bromine, and then our Br minus is our product. So you can see we can get lots of different potential types of nucleophilic substitution reactions. We just need a nucleophile, we need an electrophile, and we need a good leaving group in order for this reaction to occur. So typically leaving groups are halogens, although they can be other things as well. But really, we're just focusing on halogens here. And what's kind of neat and interesting is that the identity of the halogen itself is going to affect the rate or how fast these nucleophilic substitution reactions happen. And so the rate of the reaction is going to depend on how easy it is to break the CX bond. So remember, X is our leaving group, and that is our halogen. So X is our halogen. So we'll see in a different video that nucleophilic substitution reactions can undergo a couple of different mechanisms depending on some other factors. Both mechanisms, though, do involve the carbon leaving group bond breaking in that rate determining step. So if we take a look at bond energy as we go down that group in the periodic table, you'll see that carbon iodine bonds are the easiest to break. And it gets harder and harder. So carbon fluorine bonds actually take a lot of energy to break. So iodine would react the fastest, okay, followed by bromine, followed by chlorine, and then fluorine probably doesn't even really react very well, but it would follow that one as well in terms of the pattern here. So that is a good introduction to nucleophilic substitution reactions. That's it for this video. We'll see you in the next one.